Welcome to the promised optional portion of the lecture where we look at actually proving mathematical induction, this theorem that we're going to use so many times. And this is optional because actually knowing how to prove this doesn't really help with using it. Those are two very different things to do. So it's more, I guess, if you're the sort of person who feels guilty about using a theorem repeatedly without having proven it, then this lecture might help alleviate that guilt. Alternatively to watching the lecture, you can read the proof. But I really like this one, so I want to at least go through it in video form. And another reason I want to do it is to give you guys a chance to ask questions. So you could always use Nectar, sort of like raising your hand or something, to ask questions about things that show up in the notes or in the video. So I'm going to prove this theorem, and I don't want to do it with the fees here. You can already see that in the notes. But I'm hoping that I can make the proof easier to talk through and easier to process if you see it with a specific proposition put in place of phi, like x is green. So I'm going to actually replace all the phis by x is green, and I'll carry out the substitutions that it says here. So like this will say n is green, this will say 0 is green, this will say n is green, this will say next n is green, and this will say n is green. So let me just make those replacements. All right, there we go. So let's prove it with this kind of form. And then if you want to, you could also look at the version written in the notes and with the fees, and probably it'll make more sense after you see this. So proof. So what kind of thing are we proving? We're proving a giant if-then, right? If number 1 and number 2 hold, then this holds. So we get to assume number 1 and number 2. So let's write it, since they're nicely numbered, let's assume 1 and 2. So assume that we're in a situation where it's already been proven that 0 is green, and it's already been proven that whenever a natural number is green, its immediate successor is also green. Then our goal is to prove that all natural numbers are green. And this is Theorem 94, so let's remind ourselves of what we actually have available to us. It's not that much. Here's Theorem 94. We have basically just the definition of inductive, the definition of n, and the fact that n is inductive, and that it's contained in any inductive set. That's pretty much it. So those are the tools that we have to use. So here's going to be the trick. We want to prove that that all natural numbers are green, right? So here's the trick. We're going to define G to be the set of green natural numbers. We can do that. There might be some natural numbers that are green. We're in a context where we already know 0 is green, right? We're assuming 1 and 2. So anytime we want, we can define whatever set we want, right? So let's just define G to be the set of x such that x is or maybe a better letter would be n. The set of n such that n is a natural number and n is green. So it's the set of all green natural numbers. Then what's our goal? In terms of G, capital G, our goal is actually to prove that G is the collection of all natural numbers, right? If we want to prove all natural numbers are green, then we want to prove the collection of all natural numbers is the collection of green natural numbers. So this is the trick. So the goal now, we will prove that G equals n. Actually, this equality is two inclusions, right? And one of the inclusions is obvious. Obviously, G is a subset of n, since if something is in G, then, if x is in G, then x is in n and x is green, so x is in n. So this one is obvious. So really what is important is this one, right? This is the hard one. And this is the one we want. We want for all n If n is in there, then n is green. And that's what this inclusion would say. So actually, I'm more interested in not this equality, but just this one inclusion. Now, I do have a way of proving that n is contained inside a set. Or in other words, I do have a way of proving that a set contains n as a subset. That is this, right? If I can prove that the set is inductive, if I can prove that my capital G is inductive, then I will have that it contains n as a subset. So that's how this actually helps. That's why we define the set of green things. So we just need to prove that G is inductive. So if we can prove that G is inductive, then we get n is a subset of G simply by essence of n, theorem 93.2. So now the goal becomes prove G is inductive. Okay, let's look at the definition of inductive. There are two things to prove. To prove something is inductive, we have to prove that it contains 0 and that it contains the next of anything that it contains. So in other words, we have to prove this, but with G rather than J, and this, but with G rather than J. So let's write it as two separate claims. 0 in G, and for all n, if n is in G, then next n is in G. So let's write the proofs of these claims. Okay, 0 in G. Well, look at the definition of G. 0 in G, this is equivalent. So our goal is equivalent to, so notice I'm not asserting what I'm writing here, I'm just saying that it's equivalent to what I want to prove. So if I prove it, that would be good enough. So 0 in G is equivalent to 0 in n, and, so I'm just writing this down, but with 0 replacing n. So this is axiom 5, and 0 is green. Now, is 0 a natural number? I mean, sounds obvious, right? But everything needs to be justified. Obvious doesn't count as a justification. So we have 0 in n, why? That's actually the other part of essence of n. N is inductive, right? N is inductive. That means n has these properties of being inductive. So it contains 0 and it contains the next of anything that it contains. So that's why. By theorem 93.1, because n is inductive. And do we have 0 as green? We have 0 as green because that is our assumption. That's assumption number 1. We're assuming that the base case holds. The base case is 0 is green. That is our assumption 1. So if I just scroll up, there it is, 1, 0 is green. So that's it for that claim. 0 is in G is equivalent to this conjunction, and we've proven both of the statements in the conjunction. Now for this one. For all n, if n is in G, next n is in G. So this we'll prove by universal generalization. So consider any n in G. Then we'll try to prove next n is in G. So let's unpack what it means for n to be in G. Well, it means this stuff is true, but with n replaced by n, right? Well, here's a lazy way to do it. Then n is an n and n is green. So n is a green natural number. Now, I've used my assumption 1, the base case. How about the assumption 2? The assumption 2 says anytime you have a natural number, then if it's green, its next is green. So by assumption 2, this is universal instantiation, basically applying this to a specific case, next n must be green. So by our assumption, 2 next n is green. Okay, now have I proven next n is in G? That's actually my goal, is to prove that it's in G. Well, for next n, to have next n in G, we need, let's see, so going back to the definition of G, that's up here, we need basically this proposition here, this, to hold with n replaced by next n, right? So we need next n and natural number, and next n is green. We have one of those two. We need next n to be a natural number, and next n to be green. We have next n is, or sorry, to be in G. We have next n is in G. So it remains to prove, what's left is that next n is a natural number. It remains to prove that next n is a natural number. So why do we think next n is a natural number? Well, n is a natural number, right? And the next of any natural number is a natural number. That's because, again, n is inductive. That's one of the features of being inductive. When you're inductive, then anything in you, if something is in you, then the next of that thing is also in you. So since n is in that, it is a natural number, that was up here, and n is inductive, or here's a shorter way of writing it. Since n is a natural number, by Theorem 93.2, which is the statement that n is inductive, 93.1, the statement that n is inductive, we have next n is a natural number. And that's what was needed, right? To have next n in G, we needed these two, and now we got these two. So that proves these two claims. What was the point of these two claims? These were to prove that capital G is inductive. So therefore capital G is inductive, and therefore n is a subset of G. The natural numbers is a subset of G. So thus G is inductive, and so n is a subset of G by Theorem 93.2, which says basically that n is the smallest inductive set. So G is inductive, and n is the smallest inductive set, so G contains n as a subset. So then, for all, well, let's make sure we actually reached our ultimate goal. The ultimate thing we were trying to prove is, for all n, if n is a natural number, then n is green. Is that literally the same thing as this? Not quite. It's close, but not quite. So let's just write out the full argument. Consider any, so let me not just start a consider any out of the blue. Let me say why I'm doing this. We will now prove the ultimate goal, which is that for all n, if n is a natural number, then n is green. That was the ultimate goal, right? So consider any natural number n, then n is in G, so unpacking what it means to be in G, n is a natural number and n is green. So in particular, n is green. That's the part we need, right? And that's it. So that proves that mathematical induction works. And I hope that makes it clear that it's really a different thing from scientific induction. It's not just like, oh, it looks like the pattern is working, I bet it continues to work forever. That just seems so probable that it continues to work forever that I'm going to allow myself to just conclude that it works forever. No, that's not what this is. This is actually a theorem that has a certain proof that we just completed, and which is a consequence of all of our axioms and definitions, just like all of our previous theorems. And again, the proof you saw here was with this yellow proposition n is green, 0 is green, and xn is green, but you can imagine replacing is green with anything, really, and the form of the proof would be the same. Whether it's is green, is either even or odd, or maybe it's this statement with the x's showing up in some strange way, or this statement with the x being a dimension. That's a very common application of induction, to apply it to dimensions of things. So anytime you need to prove that natural numbers have a certain property, this is a way to do it. And I'll say one more time, I think, so I've called this the essence of n, since it's like immediately following the definition and uses the definition. But there's a good argument for actually calling this essence of n. I'm just not calling it that because it already has a name because it's so famous. But this is really the essence of n. This is what you use and is the purpose for the way n has been defined.